Problem number 10. Two wheels with fixed hubs, each having a mass of 1 kilogram, starts from rest and the forces are applied as shown. F1 this way, F2 this way. Assume the hubs are spokes. The hubs and the spokes are massless, so that we can count rotational inertia I equal m r square. In order to impact the identical angular accelerations about their respective hubs, how large must be F2? So we can use this rotational formula for angular acceleration. That's I alpha equal to Fr, and if we use expression for I is m r square, that will be m r square equal Fr. So from here we can find what is the I forgot alpha. So from here we can find what is alpha. That will be alpha equal F over mr. So to get the same angular acceleration, we just need to increase force twice if we increase radius twice. So the answer is 2n. Problem number 11. A uniform disk, a thin hoop and a uniform sphere, all with the same mass and the same outer radius, are each free to rotate about the fixed axis through its center. Assume the hoop is connected to the rotational axis by light spokes. With the objects starting from rest, identical forces are simultaneously applied to the rims as shown. Rank the objects according to their kinetic energy after a given time t from rest to greatest. So all three objects are in the same condition, so we can just compare their final kinetic energy. So kinetic energy equal 1/2 I omega square. So we need to find what is expression for this kinetic energy. So to find what is omega, that's angular acceleration multiplied by time. And the angular acceleration we can find from regular expression I alpha equal Fr. So it means that alpha equal Fr over I, omega equal Frt over I, and finally kinetic energy equal 1/2 I F square R square R square T square over I square. So one time I is cancelled, and we have kinetic energy equal 1/2. Same expression for all of them on the top, and on the bottom we have different I. So we have for greatest moment of inertia we have least energy. So it means that correct answer will be, we know that for disk we have I disk equal 1/2 m r square. For hoop we have, that's m r square, and for sphere we have I sphere equal 2 over 5 m r square. So the least I is for sphere, for greatest I for hoop, and this in the middle. So it means that for sphere we have, for hoop we have least, for disk that's next one, and for sphere we have greatest kinetic energy. So that's the correct answer. Problem number 12. A 2 kilogram rock is suspended by a massless string from one end of the uniform 1 meter measuring stick. What is the mass of the measuring stick if it is balanced by a support force at the 0.2 meter mark? To solve this problem, we need to write equation for static equilibrium. So for this we need to write torque from the left, which is mg by 2.0 meter, and that's equal unknown mass m g multiplied by distance from center of gravity for this stick, which is right in the middle of the stick. So it means that this distance is 0.3 meters. So to calculate what is total mass m, big one, that will be m 2 over 3, which is 1.33 kilogram. So from here we have C, correct answer. Problem number 13. A particle moves along the x-axis. It collides elastically head-on with an identical particle initially at rest. Which of the following graphs could illustrate the momentum of each particle as a function of time? We know that during absolutely elastic collision of two identical particles in one dimension, 1D, they after collision they will exchange momentums. So it means that the first particle moves and after it stops, and after collision a second particle start to move with the same momentum as the momentum of the first particle before collision. If we check all graphs, we can see that only on graph D we have this situation. Second particle not moving, first particle has impulse p, momentum p. After short collision, second particle move with the same momentum as the first particle before collision, and the first particle just stop. So D is correct answer.